Hello everyone. Well, thus far we have math models for all of our energy storage mechanisms. We can calculate an amount of elastic potential energy, 1/2 kx squared. We can calculate an amount of gravitational potential energy, mgy. We can calculate an amount of kinetic energy, after our last lab, 1/2 mv squared. And we can calculate an amount of dissipated energy, force of kinetic friction times the distance. But what we haven't talked about yet is the energy transferred into or out of a system by means of an external force. Or in a word, that's right, the amount of work. Right, so how do we calculate the energy that gets transferred into and out of a system that we show in our energy flow diagram when we're doing LOL diagrams? Well, let's do an example here and we'll see how we're going to calculate this amount of work, this amount of energy transferred. Here we have a box that's going to be pulled horizontally by a nice horizontal applied force, a distance d at constant velocity, like so. Watch it again. Being slid across the floor at constant velocity by that applied force. Well, we've done problems like this. I mean, we could do this with Newton's second law and a kinematic equation and those kinds of things, but we could also look at it from an energy standpoint. First thing we have to do is to define our system. So let's put the box and the earth in the system. Now, is that an isolated system, meaning no external forces? Hopefully you see that this is not an isolated system, because this applied force, which in our diagram clearly pierces our system boundary, it's very visual, right, is in fact exerted by something that is outside of the system. Whatever is applying this applied force, it could be me pulling on the box, it could be you, it could be a car that's hooked up to it, but whatever it is, we don't know what it is. And it's something outside of the system, and therefore it will do work, as we will see. How much work? Well, let's figure it out. Let's take a look at this from a pie chart standpoint. And for a pie chart, I'm going to look at 3 different places: when it first starts, somewhere in the middle, and then at the end. Now, not before it starts and after it ends, but while it's moving at a constant velocity. So pi 1, there's pi 1, is going to be filled with kinetic energy because it's moving. It's moving at a constant velocity. No EG because it's on the ground, no EE, no springs or anything, no EDIS because nothing's happened yet. Since it's moving at a constant velocity, the amount of kinetic energy it has when it starts should be the same halfway, same at the end. So we should have the same amount of EK. Now, EG doesn't change. There isn't any because it's on a horizontal surface. EE doesn't change. There isn't any because there aren't any springs or rubber bands. But is there some dissipated energy later on? Well, if you know the EDIS math model, you know that 2 things have to happen. You have to move the box through a distance d, which obviously we do, and there must be a force of kinetic friction. So to decide if there's dissipated energy, you have to decide if there's friction. Now, I didn't say whether there was or not in the problem, but think about the forces. I'm not going to bother to draw the force diagram here. Hopefully you can think through it. If there wasn't any friction, this applied force would be unbalanced, and it would make the box accelerate. But the box isn't accelerating. It's moving at a constant velocity, and therefore the forces must be balanced, and therefore there must be a force of kinetic friction. Think through that again. There has to be kinetic friction acting between the box and the ground in order to put the forces in balance so that there's 0 net force, 0 acceleration, constant velocity. And since there's friction, that means the box is rubbing against the ground, there's going to be energy dissipated. Thermal energy, sound, things like that. Now I'm going to do this a little weird here, but just for our purposes, I want to keep the EK the same amount, so I'm going to actually take my pi and just make it a bigger pi, and that outer ring is all filled with dissipated. And when we get to 3, it will dissipate more energy, so we have an even bigger pi filled with more EDIS. So the same amount of EK the whole time, but an increasing amount of EDIS. So you can see here that clearly energy is not conserved. The energy is increasing. There's energy being added into the system. So energy is flowing into the system because of the external force, F of A, and in this case, it's being stored as dissipated. Now, only in this case, because the forces are in balance because it's moving at constant velocity. If you pulled a little harder, then the applied force would be bigger than friction. You'd have a net force and you'd have an acceleration. And then not only would E dis increase, but the kinetic energy would get bigger and bigger as well. But in this simplified case, constant kinetic energy increasing E dis. So how are we going to figure out the amount of work? Well, the work is being done by this external applied force. So let's think about what we know about this force. Because we're pulling this at constant velocity, the force would have to be constant. And since it's pointing to the right, it would have to be positive. So let's make a graph of that applied external force versus position. Remember, x is position. It's a vector graph, right? Since the applied external force is constant, that means the graph is going to be horizontal. Right? Means it doesn't change. And it's positive, so it's above the position axis. So this is what the graph would look like. Now, I want to look at this graph, and I want to apply something, some property of this graph, to stand for the amount of energy being transferred into the system, the amount of work. Well, as we saw a moment ago with the pie charts, the further we pull the box, the more work is being done, the more energy is being transferred. So we need to look at something on the graph which gets bigger and bigger as we pull the box further and further. Hopefully you notice, indeed, the area under the curve seems to get bigger and bigger as you pull the box further and further. So, if we're going to define work as the transfer of energy into or out of a system by means of an external force, we can also define work graphically to be the area under the external force versus position graph, where this is the external force that is transferring the energy. So you'll notice this is similar to how we did potential energy functions, but a little bit different because it's different forces. It's already a positive amount of energy, so we don't need to do the negative of the area under the curve, just the area under the curve. Now, if we pull a distance d with a force we can call F of A, this area is, of course, a simple rectangle. And you've known for a while that the area of a rectangle is simply length times width. So the amount of work that is done on the system, the amount of energy transferred into the system in this case, is equal to this dimension, which is F of A, times this dimension, which is d. And there we go. That is the amount of work for a constant one-dimensional external force. Notice the units: force in newtons, distance in distance in this case in meters. So these are Newton meters or joules. So this is an amount of energy transferred in or out. Now, if this was regular physics, that'd be good enough. But at least in AP, while we're going to stick to constant forces, we can, honors at least, we can stick with constant forces, but we can also make the direction a little more complex. Okay? We're still going to use this definition, but we're going to factor in a little bit of trig here. So let's do a little more complex example. Here we have the box being pulled by an applied force at a constant velocity, a distance d, but the applied force is at an angle theta. The system would, of course, still be the box and the earth. There it is. It still won't be an isolated force, but before we do that, let's draw the force diagram just quickly here of the box. There's the box. What forces act? Well, we've got this applied force acting at an angle theta. Since the axes here are horizontal and vertical, we need to know how much of that applied force is horizontal. There's F of AX. And how much is vertical. There's F of AY. The ground is also supporting the box, which would be an upward normal force. And the earth is pulling down on the box, which would be a force of gravity. Notice that we have not one, not two, but three vertical forces. F of G, F of N, and F of AY. So how big are these three forces? Well, it's not accelerating up and down. In fact, it's not even moving up and down. So the forces must be balanced, the three forces. So F of G, down, has to balance out F of N plus F of AY, up. So notice here, part of F of A is being used to put the vertical forces in balance. Now, we also have a frictional force, which we talked about a moment ago. Since we're pulling the box to the right, it's going to act to the left. And friction would have to balance out F of AX because it's moving at a constant velocity horizontally, no acceleration. So notice here, the entire applied force is not being used to move the box. Some of it is being used to balance the vertical forces. Only F of AX is moving the box. And notice here, F of AX is the part of the force that's in the direction it's moving. Let me say that again. F of AX is the portion of the applied force which is in the same direction as it's moving, in this case, horizontally. And that F of AX force would be constant and positive. So if we graphed that force, it would be a horizontal line above the position axis. And if we pulled it a distance d, here's F of AX, we'd still have a rectangle of area. That would be length times width. And using the same definition, this area must be the amount of work done, except now the length is F of AX times d. Well, what does that change? Go back to your force diagram, and let's redraw F of AX in terms of F of A. F of A is the hypotenuse of the right triangle, theta is the angle, and F of AX is the adjacent side. So F of AX can be written as hypotenuse cosine of the angle. Again, hypotenuse cosine of the angle is the adjacent side. Since these are all multiplied together and multiplication is both associative and commutative, I could rearrange this and write it as F of A times the distance times the cosine of theta. And if I want to make it a little generic here, because the applied force, the external force doesn't have to be applied. It could be whatever force is external. I'm going to rewrite this here as the external force times the distance times the cosine of theta. Let's be careful about what we mean. Right? This has to be for constant external forces because this area is a rectangle. For those of you in calculus, of course, if our external force was some function of x, some curve, right? This is an integral, and we could still integrate it as long as we had the function. We're going to stick to constant forces in here, however. And theta we define as the angle between the external force and the displacement. Notice here the displacement is horizontal, and the applied force is at that angle theta. So theta is not just any old angle. It's the angle in between the external force and the displacement. Now, let's look at a couple of examples here to see how this cosine of theta works in this function. Let's say we have a case, like our original one, where you are pulling the box horizontally while it's moving horizontally. So, it's moving in the same direction you're pulling. According to this equation, then, we need theta, the angle between these two. And since they're in the same direction, the angle between is, of course, 0. That's the angle in between two things that are in the same direction. And hopefully you know that the cosine of 0 is 1. Plug that into the equation, and you get F external times d. The entire force is being used to move the box. The entire force is in the same direction as the displacement. And so this is how you get the maximum energy transferred into the system. You're using all of your force to transfer energy. What if it was this situation? The box is moving to the right, but you're pushing against the box, which might do something like this. It might cause the box to slow down because you're pushing against it. Now what's the angle in between the direction it's moving and the direction of the force? Well, if they're in opposite directions, the angle is 180 degrees. And the cosine of 180 degrees is -1. So now you get negative external force times distance. Again, this is a maximum amount, but a negative work doesn't mean the other direction, because it's not a vector. It means you're transferring energy out of the system. I mean, think about it this way. The box Earth system starts with kinetic energy, but over here, it has no kinetic energy left because you've stopped it. So you end up with less energy at the end than you started with. You've transferred energy out of the system. So positive work means energy added in, negative work means energy added out. And if you look in between, right, when your cosine of theta gives you a positive number, it means you're adding energy. When it gives you a negative, you're taking it out. Now let's look at the other extreme. And this might be hard to figure out how you would do this, but what if you were pulling up while the box was moving to the right, like so? Okay, so somehow you were applying a force upward while it was moving to the right. Now, the angle in between these, clearly 90. And the cosine of 90 is 0. So how much work have you done? None. You haven't transferred energy into or out of the system because none of the force is being used to move the box. There is no component of this external force that is in the same direction as you're moving. And that's how you figure out how much work. It's the amount of force times the amount of distance in the direction you're moving. How much force is in the same direction that you're moving. And like I said, in between 0 and 90, you get a positive amount of work, although shrinking as you get closer to 90. And from 90 to 180, you get an increasing amount of negative work, energy taken out of the system. It's kind of cool how the equation just gives you that, so long as you realize what the angle theta means. And of course, once we know the amount of work, we can control show how much work is going in or out on our energy flow diagram as part of our LOL diagrams, which will allow us to solve problems in which work is being done. Tomorrow you're just going to do a worksheet that asks you to calculate works and asks you some conceptual questions about work, and then the next day we'll start using that in problems. So I hope you enjoyed this rather lengthy video on work.